Hey everybody, I hope you're well. I'd like to welcome you to the May edition of the Audio Programmer Meetup. This is awesome because I believe this is the 3-year anniversary that we've been doing this. Having a monthly virtual meetup for 3 years running, I'm really appreciative. First of all, of everybody that's joined us, and also the presenters, everybody who has joined us to share their insights and their perspectives on audio software development. I'm really proud of what we've done here, and I feel like we could do more. So 3 years running, here we are. Today we have two very special guests with us. We have Ben Vining, who is a audio software engineer specializing in DevOps, one of our favorite things about audio software development, building installers and notarizing and code signing plugins. How are things going, Ben?
Things are going pretty well. I have been working on several DevOps projects lately, so this is definitely like very timely for me. I'm just basically talking about like a lot of the work that I've been doing recently.
Fantastic. And we also have Geraint Luff from Signalsmith Audio, who has been a special guest on the channel a couple times now, and he's back to talk a little bit about Waveshapers and how to make them sound better. How are things going in Cambridge, Geraint?
Things are good. Little manic day to day, but it's good to be here.
Yes, thank you for joining. So just a couple quick announcements before we go ahead and jump into the talks. First of all, if you haven't joined our audio programming Discord, I hope and invite you to come join us. We have nearly 9,500 audio software developers of all different skill levels, all different ages, from all around the world. And there's always a lively discussion happening in there. And you can join us at theaudioprogrammer.com/community. We also have a jobs board. So for people that may not know, we have a recruitment service and a contracting service for audio software developers where we help link them up with opportunities. And if you're looking for an opportunity, you can find the latest job posts on theaudioprogrammer.com/jobs. If you're a company that's looking for an audio software developer or anybody else within the industry, so DevOps, front-end engineers, product managers, all those things, we help companies out with all of those types of roles. And if you get in touch with us on theaudioprogrammer.com, we can help you out. Next week, I will be traveling to San Francisco to hang out with the ADC crew. So for anybody that isn't already aware, they're holding a meetup, an in-person meetup in San Francisco called ADCX. It's really awesome. They're still selling tickets for a couple days longer, and I hope to see you there. If you're in the San Francisco area, or if you have the money to travel in, come hang out. Let's grab a coffee, and you can buy the tickets on audio.dev, so that's audio.dev. Go grab your tickets. And thank you as well to our sponsors, Focusrite and Sonics, for sponsoring the Audio Programmer Meetup. Without you, it wouldn't be possible. Thank you very much for sponsoring the Audio Programmer Meetup. And with that, let's go ahead and jump into our first talk from Ben Vining. So as I said before, Ben is an audio software engineer who specializes and has a particular passion for DevOps. So that is using CMake, the pipeline that is outside of the core audio software development for actually building installers, being able to run plugins on other machines other than your own. And today he is going to be talking about packaging audio plugins with CMake and CPack. So over to you, Ben.
Thanks, Josh. Can we see my slides? I try to share my screen.
Yep.
Okay, great. So as Josh mentioned, my name is Ben Vining, and my topic today is packaging audio plugins. And so this is kind of a twofold topic. We're going to be talking about building your actual installers that you distribute. But then, like Josh mentioned, if you want to actually run your software on other machines, On Mac and Windows specifically, they will throw up all sorts of warnings if your stuff is not code signed. And then on Mac, it also needs to be notarized. So we're going to go through how we can integrate all of that with our workflow. So these are the 4 main topics that I'm going to cover today. What I am not covering today is the basics of CMake. So I'm going to assume that you understand the basics, at least, of CMake scripting and CMake cache variables. And a prerequisite for most of this is that you're already using CMake to build your project. You technically can use CPack on its own, but I don't recommend it. It's going to be much easier if your build information is already all in CMake. And if you don't have any prior experience with CMake, I recommend there's a couple different talks you can find on YouTube, including a couple ones that I did on Josh's channel a few months ago. So definitely brush up on the basics and then come back and watch this on YouTube later once you've got your actual build up and running. So first of all, what is CPack? CPack is a tool that is part of the CMake tool set. So CMake is actually 3 different executables. The CMake program itself, you run to configure your build and generate your build files. And then CMake also has a -- build command line signature that you can use to actually invoke the build. And then there is a CTest executable for running all your tests and reporting results. And then the CPack executable builds installers for you. And all 3 of these are in the CMake packages. So if you've installed CMake on something like Homebrew or pip, then you probably already have CTest and CPack on your system. And CPack borrows a lot from CMake's philosophy. So CMake allows you to describe your build in a very high level, abstract scripting language, and that is platform agnostic. And then when you go to actually build the project, you select one of CMake's generator backends. So if you're on a Mac, that might be Xcode or Visual Studio on Windows. And then that takes your platform agnostic build description and creates platform specific build files. CPack is very, very similar. You describe what to install and how in a platform agnostic way, and then they have different backends that are platform specific, and they're also called generators. And there are lots of different ones available on Mac. You can build PKGs or DMGs. They also have a backend for the Qt installer framework, which allows you to create installers that look exactly the same on every platform. And then you can also do things like build deb and RPM packages for Linux, or even just create like regular tarballs. But usually for audio plugins, most of the people that I have worked with are most interested in distributing PKGs on Mac and EXEs on Windows, usually built using InSys. So those are the ones I'm going to focus on today, but a lot of this info really should work if you would rather build a DMG, whatever. The whole point of CPack is that you can basically switch out what you're generating, but all the information that you specified can stay the same. So why do we care about this? Why would we want to use CPack? Well, the first reason is that if tomorrow a new fancy installer generating framework becomes available, then we can expect Kitware to release a backend for it for CPack. And so we don't have to learn all the new configuration file formats and whatever for all the different tools. We can just specify our information in one place and have CPack translate it into configuration for all these different third-party tools. Another reason is for simplifying and unifying our CI workflows. So if you're currently building your installers in a custom way, then you probably have a shell script on Mac and maybe a PowerShell script on Windows. And so you probably have something in your CI like on Mac, run this, bash or ZSH or whatever. And then on Windows, you're going to invoke PowerShell. And none of that is necessary with CPack. These 4 lines that you see here is going to be exactly all you need to run to build your product and your installer. And this is going to be exactly the same on Mac and Windows. And I view this as a really big advantage because it cuts down on CI configuration and debugging between platforms, because the way that you're calling your tools is going to be exactly the same on every platform. So before I go into too much more detail about how we actually use CPack, I want to take a moment to discuss installing in CMake in a more general way and how it works and what it means. So when we say we're going to install something, basically what that means is that we're going to take a file and copy it to another place. So usually what this means is that we're taking some file that is in our binary directory where we've compiled everything, and then we're going to copy it to another place on the system so that it can be found by our terminal or by other builds if it's a library we want to install. And so we tell CMake of what we want to install using this command right here that says install. And here's a couple examples of it. We just tell it what we want to install. We give it a destination, and then we can specify a component. That's optional, but I recommend that you specify components. And in this second example right here, we can already see one benefit of using CMake and CPack together, because we can just give it target names. And so when we just say targets my app, CMake will take care of resolving the full path to whatever artifact my app produces. So it may just be an exe on Windows. It might be a .app bundle on Mac. CMake will take care of that. And all we have to do is say, take this target and all of its payload stuff and put it into this destination. Components make things convenient for your users. So basically what this does is in the final installer, if it's a graphical installer, like an app that's running on Windows or a PKG on Mac, then basically the user will see a list of all the components and can check and uncheck the different ones that they want. So if you put all your different plugin formats into different components, then that allows your user to say, for example, like, I'm only working in Pro Tools. I only care about the AAX. I don't want any of this other stuff on my system, only install the AAX. And then that's exactly what they'll get. So in our CMake, we call these install commands to take something and say, when it's time to install it, we're going to copy it into this certain destination. And when you actually call this install command, what CMake actually does is it generates a script that will copy those files when that script is executed. And so as it turns out, because it is just a script that copies some files, we can run that script without building a full installer. So if you've ever looked at the docs for the CMake command line tool, you may notice it has this -- install subcommand. And basically what this does is it copies all of it executes all those scripts to copy all of the artifacts that should be installed into their destinations. And this command, I just wanted to mention because this is what you will use if you are building a library from source that you want to have available on your machine. You'll typically clone the sources, configure CMake, build CMake, and then run this to take the library binaries you've just compiled and copy them into your system directories so that they can then be found by other builds. And so this is convenient to know about, and also to just kind of wrap your brain around how installing works in CMake, because the core point here is that it's basically just executing some scripts that copy some files. And as it turns out, this is actually how CPack works under the hood. CPack is just going to execute this CMake install command in a temporary directory, and then look at all the files that got written there, and then wrap them up into a tarball or DMG or whatever. The most important thing to know about installing in CMake is that destination paths must always be relative. The reason why is because CMake allows the user to override the install prefix. So if we just think about our previous example with that CMake -- install, right? By default, having it right into our system directories makes sense, because I just described, like, if you just want it installed to your system and everybody can find it, then that's great. But imagine, maybe you want to have different versions of the same library on your system. Or maybe you're a package manager and you want to have all the artifacts for a particular project in some directory so that you can keep track of everything. You want to be able to basically redirect that command and say, don't install to the root of the system, install to this other directory. And so in order to support that in our CMake projects, we need to play nice and specify relative destinations. So these are two examples that are both correct. So this here, there's no leading slash on this include. This is a relative path, so everything is good. And then here we're setting our destination based on whether we're on Mac or Windows, but either code path has a relative path. And so either way, this will end up being a relative path and everything is fine. These are some examples of incorrect paths that are absolute. So here we've got a leading slash on include. And so what this will do is, even if the user tries to override the install prefix and say, go to this directory instead, this will refuse and will stubbornly just always write those two header files into the system's root include directory, no matter what. And that's really inconvenient. So that's why we always want to make sure to have relative paths here. And again, we don't want to be hard coding things like drive letters on Windows. It'll usually be C, but it might be D. Other users might have other drives set up. And so we just want to say program files and then allow the user to specify what their actual root path is. So when we are installing audio plugins, one of the most difficult or complex pieces of the puzzle is that we've got all these different formats and all of them want to go in different places. And they have different defaults for Mac and Windows. And I've shown the most common default locations here. Linux is kind of another story. I haven't bothered to include those. And of course, there's no audio units on Windows, so they don't go anywhere. But also notice all of these are relative paths. So we're being quite specific. We're saying program files, common files, Avid audio plugins. That's a very specific location, but it's still a relative path because we have not hard coded a drive letter here. And then also there's no leading slash here. So this is still a relative path relative to whatever our root is. So if we want to encode all that logic into CMake of like putting different formats into different places, the first thing we need to do is set up some variables that are going to hold the destinations for each possible format. So I'm setting these as cache variables here. So I'm assuming that everybody at least has kind of an idea. These are persistent settings that can be overridden by the user, but have a default if the user does not specify overriding any of them. So I'm basically setting some temporary variables here and then assigning the cache variables default values based on whether we're on Mac or Windows. And then here, the audio unit one, I only need to set on Apple, so I can just go ahead and set that here. So hopefully this makes sense so far. We're just setting some variables that are going to hold our destination paths as relative paths for each different format of our plugin. And then I want to take this information and basically write a helper function that we can call that will install all the different formats of our plugin into each destination for each format. So how do we do that? So just a quick note about the Juice CMake API. As it turns out, when we call Juice add plugin, it actually creates several different targets. And you may have noticed this, like in your Xcode list of targets, you might have noticed it has this naming convention. So this name here, this my plugin, will actually be a static library that compiles all of your Juice modules and any source files you've added to your plugin. Those get compiled into a static library that we call kind of like the shared code of the plugin. And then the actual plugin format targets are separate targets that link to this static library. And fortunately for us, Juice uses this very consistent naming convention. It's always the name of the plugin and then underscore and then the name of the format. And also, fortunately for us, Juice sets a target property on this shared code target that contains a list of all of the active format targets. So Juice is going to set on my plugin a property that contains this list: my plugin standalone, my plugin VST3, AU, and AAX. And that is how we are going to achieve writing a function that we can call and send it just like the name that we sent to Juice add plugin, and have it actually install the actual formats. So this looks a little bit scary, but I'm just going to go through this line by line. And most of the complexity here actually has to do with getting the list of formats and then processing those. And so if we just ignore these first two lines real quick, this get target property here, we're retrieving that property that I just mentioned. So this Juice active plugin targets property holds a list of names of targets. So this list is going to be my plugin standalone, my plugin AAX, And so once we have the name of the format target, we want to figure out what format we're building so that we can pick the destination based on the format. And because Juice uses this very consistent naming scheme with just like the plugin name and then underscore and then the format name, we're basically just doing a little string manipulation to chop off the plugin name and the underscore and be left with just the name of the format. So it looks a little bit strange in CMake, but just trust me that this works. And then here, this basically is like a switch statement in C++, but CMake doesn't have those. So we get to do big, long if-else chains. And so here I'm just referencing those cache variables that we set up earlier for each format. And so I'm saying, I'm iterating through the list of format targets that are being built for this plugin. And for each one, I'm figuring out what format it is. And then I'm picking a destination that's appropriate for that format. And then I'm going to actually call install. So then I need to tell install the format target. And then I gave it the destination. And then we're going to create an install component for this format. And then we actually create that install component here with CPack add component. And then we can do some customization, like giving it a display name, a description, and then we can also create a component group and package together like all the different formats of our plugin into a component group here. And you can get as fancy with this as you want. Like if you wanted to have different long form descriptions for each format, you can do that. Here, I've just done a real basic, like install the standalone format of the my plugin plugin. Just because that's really easy to do with these variables that are available to us here. But the point is that now we have a very simple function that we can call. So in the actual user CMake list.txt, all we have to do is say juice add plugin, and then this install plugin, my plugin, and then include CPack, and we're done. So if you just want to get a basic installer building as kind of like a proof of concept to distribute to your friends, this is the slide that you should take a screenshot of, because with just the code on this slide, you can get a working installer or an almost working installer. You may notice that there will be some Juice stuff in there because Juice also sets up install rules. And the way to get rid of any extra stuff is there's a variable called CPack components all. And basically what this means is it's everything that is going to be included in the installer, which by default is everything. And so if you set this to just your plugins install components, then your installer will contain only your plugin and nothing else. So the way to get rid of juice stuff is to set CPack components all to just your plugin install components, whatever you've named them, before you include CPack. And so then you'll have all of your plugins and it'll be clean and nothing else in your installer. And then you might notice that some of your payload paths might have something prefixed to them. So like if you're making a PKG on Mac and you've said your standalone should be in applications and everything else should be under like library, audio, whatever, you might see that it actually wants to put the standalone in applications, and the libraries in applications, library, audio. And the reason for that is because these CPack installers, they have some default prefixes set for the user's machine. So usually if you're installing a GUI app, applications is where you want it to go. But because we're also putting things in library, we want to basically be working from the root. And so we're going to set this to basically just a slash, and this makes sure that nothing gets prefixed to our paths on the user's machine. Little hand wavy. Hopefully that makes sense. I'm debating explaining this a little bit more in depth, but I don't want to confuse anybody. I mean, it's a little bit confusing because it might seem like this is like an absolute path, but really the key here is that we're talking about on the user's machine. So like when they're actually running the installer, this is something that gets prefixed to everything. And so basically we just get rid of that entire process by just saying like nothing should be prefixed. And then the last hint I'm going to give here is I really recommend looking up all the available configuration variables for CPack and for your specific CPack generator that you're using, because they're quite configurable and they allow you to set lots of like branding text and images and icons and background images. And, you know, you can really go all out with it if you want. And so I really recommend just kind of looking through and seeing what you can configure for your use cases. So that's building our installer. But if we actually want to be able to distribute our code, we need to take some extra steps to make sure that our users aren't going to get malware warnings when they try to install our stuff. So I'm going to talk about code signing and notarizing specifically on Mac OS for today. Windows will follow a similar process, but it is a little bit more specific to your exact setup, whereas macOS has kind of like the same steps that everybody uses. So I'm going to talk mostly about signing on Mac today. And a really big shout out to Sudara, who wrote a wonderful blog post on melatonin.dev. And a lot of this is based on that blog post. And that post also explains a lot of details of code signing in more depth than I have time to go in today. So I really recommend reading that blog post. But the basics, what it boils down to is that your plugin binaries themselves need to be signed with code sign. And then your installers need to be signed with product sign and then notarized and stapled. I think you technically can sign your installers with code sign also, but I typically use product sign for installers. I find it easier to get working. So obviously the first step when we want to integrate any sort of scripting stuff into CMake is to figure out what commands we need to run. What are the shell commands that you would run manually if you were doing this? And luckily for us, Sudara has provided these on the blog post. So we can pretty much just take each of these commands and figure out how to get CMake to execute them for us. So we don't really need to worry about the details of all these different arguments, because I'm mostly going to be talking about how to get CMake to do it. And then once you understand that, then you can tweak the options for exactly what you need. And it's also applicable to other types of build steps you may want to do. So signing our plugin binaries is actually fairly straightforward. We basically want to sign them every time they get built. And CMake supports this very, very well. There is this add custom command on a target signature that basically says post build. So what this means is that every time this target gets built, then we're going to execute some sort of shell command, and it can be anything, but here it's going to be code sign. So just like we did earlier for defining our install rules, we're going to have a sign plugin function that just takes the plugin shared code target. And just like we did before, we're going to get the full list of all the format targets out of this property, and then we're going to iterate through each of those. And on each format target, we're going to read another target property that Juice very conveniently sets up for us. And this property tells us where the actual plugin artifact is going to be after we build. And this is very convenient that Juice does this because different plugin formats might actually have different kinds of artifacts, right? So this might be, if you're building a standalone, it might be an exe file on Windows. It could be a .app bundle on Mac OS. And then it could also be like an AU component, VST3, directory or bundle, or whatever they are these days. It doesn't even matter. The point is we can just evaluate this target property here, and CMake will know how to expand this path and get the actual plugin artifact to work with. So the only input variable here is going to be our code sign ID. And so if you're working in a private repository, you could just hard code your ID as the default here. Otherwise, you probably want to do some sort of checking to say, like, if this is empty, then we can't do the code signing, and but this is the bare bones of how we actually implement this. And so just like with the install plugin function, we can now easily call sign plugin and get this post build code sign command added to all of our plugin targets. Signing our installers is a little bit more complex because the installers don't actually exist until we've run CPack. So really, we want to be able to run a script after CPack has run to post-process the installer binaries. And as it turns out, CPack actually supports this out of the box. You can set a variable called CPack post-build scripts, and it holds a list of scripts, so you can have as many as you want, and it will execute each of them once it is done building your installer. And so it'll basically send the script a special variable with the path to the built installer so that it can work with it. Because we are not in control of how these scripts are being called, and we can't specify like other variables to send into them and stuff, then basically any other information we want to get into this script, we have to basically hard code as text. And so you may have seen a CMake command before called configure file. This command takes a file and evaluates variable references as text and then saves this as a new file. So this is a way that we can get information into our post-build script. Basically, we're going to have some input variables that we want to substitute at configure time when we run configure file. And then we're going to take the scripts that was generated that had the stuff substituted, and that is what we're going to have CPack execute as our post-build script. So this, again, it might look kind of scary, but most of the logic here is just dealing with the fact that product sign can't work in place. But so this is the content. This is a file called signinstaller.in. And during CMake configure time, we're going to call configure file with this as the input. And anything that is in between @ signs is referencing a variable, and that is going to be replaced with the variable's value when we call configure file. So the regular variable references here, the $curly brace, those are going to stay as is, but anything in between two @ signs is going to be replaced with that variable's value. And then the new version of the script is going to be saved, and then CPack is going to execute that as the post-build script. As I mentioned, the annoying thing about product sign is that it can't work in place. You have to give it different paths for input and output. So basically what we're going to do is we're going to take the installer artifact and rename it in the same directory. So I'm just getting its the directory that it's in, and then its file name, and then I'm basically adding -unsigned to the file name, and then copying it from where it was originally into this new file name, removing the original one, and then calling product sign with this unsigned path as the input, and then the original path as the output, and then removing the unsigned one. So now what we've got is the installer artifact back where it was originally that has now been signed by a product sign. It's really annoying. I wish product sign could work in place, but unfortunately, this is what we have to do for now. And so the way that we use this in our actual CMake list.txt, all we need to do is declare some variables here. All of these cache variables are the input variables, which are in @ here. And then we just call configure file, and then add the file that was generated into this CPack post build scripts variable. So in configure file here, this @only argument is really important because that makes sure that these $curly brace are going to stay exactly the same as they are. And we're only going to replace what's in between the @ when we're configuring this script here. So this might be a bit confusing, especially if you're not super comfortable with CMake. But the key takeaway here is that this might look very much like what you currently have in a shell script if you're currently building your installers manually. Basically, all we've done is we've taken these shell commands and we've translated them into CMake execute process calls. And then our input variables here that are known at CMake configure time, we are using text replacement to configure this template file, which will create an actual script that CPack will then execute. So hopefully we can follow along with that. And on Windows, only the actual installers need to be signed. So as far as I know, on Windows, your plugin binaries themselves don't need any kind of post-build steps. We only need to actually sign the installer. And the exact command that you use for that will depend on your certificate, the exact type that it is, where it's hosted. And Sudara also has a blog post about Windows signing, and it goes into some more detail there. But once we have implemented all of this, we are able to have this workflow that I described at the beginning. So now we can use CMake to configure our project, to actually build our project, and then we can call CPack and get a PKG on Mac and an exe built with NSYS on Windows. And these 4 lines are all you need, and they can be exactly the same on Mac and Windows. Thank you very much. And I will take some questions if there are any.
Fantastic. Thank you very much, Ben. And at the moment, we have one question from Brady asking if the install_plugin CMake code would be available anywhere to avoid some transcribing.
Yeah, sure. I do have a repository on GitHub called Oranges that has some like CMake code that I reuse in several projects, and I haven't had a chance to update it in a while, but this is definitely something that I'll put on there.
Fantastic. And a question from Kostas, who is asking, is it possible to set those code signing variables using GitHub secrets for GitHub Actions?
Yes, that's exactly the way that I do it. So if you have a secret that you want to get in to CMake, there's basically 2 different options for CMake to retrieve some information from the outside. You can either use a cache variable or you can read an environment variable. I usually use cache variables because they are persistent, right? Like if you run CMake more than once, you only need to specify the cache variables once. Although for CI, you will probably be doing a fresh build every time. So you could also use environment variables. But either way, however you're reading them from within your CMake, yes, absolutely. In your CI, during the CMake configure step, I would set those variables with the values of your secrets. And GitHub Actions is really smart about, like, in their logs, they obfuscate your secrets if they find them anywhere. So like in your CMake, if you're doing some kind of verbose printing to say, like, you know, here's the code sign details that will be used, here's this, here's that, the logs will still obfuscate those. It will know, like, oh, I need to hide that string because that's a hard coded secret. So yes, absolutely. I would, in your YAML description of your GitHub Actions, I would reference the secret value, pass it into CMake using -d in the configuration phase to set the value of a cache variable. And then, yeah, use those cache variables when you're setting up your code sign commands.
Fantastic. Another question from Brady, who asks, have you talked to Sudara about putting this into their pimple juice template?
Not yet. Yeah, I might be interested in contributing to that. I'll definitely have to talk to Sudara about that.
Yeah, big shout out to Sudara.
Yeah, those blog posts are really, really fantastic. They have a lot of detail. Really, really great resource.
Yeah, Sudara is awesome. Cool. Thank you so much, Ben.
You're welcome.
Great. And for anybody who's looking to possibly present on the channel, we always offer slots for anybody who is interested in presenting their perspectives on audio software development, whether it's your first university project and you just want to share it with the world, or you're a person who's been in the industry for a long time and you want to share some of the things that you've been working on with your work in the company. You can join us. Once again, the website is theaudioprogrammer.com/meetup, and then in there's a submit a talk link there. So no matter where you may be in your audio programming journey, come join us and hang out, and we hope to get some more submissions. So moving along, we next have Geraint Luff. Is it Luff or Luff?
It's Luff.
It's Luff, yes. Geraint Luff from Signalsmith Audio. So if you've been a follower of either the Audio Programmer YouTube channel or also the Audio Developer Conference, he has presented several fantastic topics regarding DSP, and he is back again to talk with us about distortion and wave shaping. So the title of this talk is called Warmer Waveshapers. Take it away, Geraint.
Thank you. I'll just share my screen. Hopefully this is going to work.
By the way, we haven't had a chance to do a sound check before this, so
oh yeah,
it's going to be playing any sound. We may need a moment just to get that right, but we'll go through the talk and see how things go as needed.
okay, so I'll just oh, hang on, sorry, my Zoom settings have just gone somewhat awry. I'll just oh my goodness. External advance. Great. Okay. So hopefully you can see this.
Yep. All good.
I can't actually. Can you see this, Josh? I can't
Yep.
hear you or Ben anymore.
Yeah, I can see it. Can you hear me?
Great.
This is so funny. One second, we're just having a technical difficulty here, a unique one.
All right.
Can you hear us now?
I can, yes.
Okay,
Yeah.
cool. That was funny.
Okay. Yeah, so this is not going to be a comprehensive exploration of Waveshapers or a grand thesis on what makes one good. Instead, I'm just taking aim at one particular thing that I don't like about Waveshapers, and a couple of related effects as well, and talking about the ways that I personally like to tackle that. So I expect that this crowd might already know what wave shaping distortion is, but I'm going to start with a definition anyway. So wave shaping is a method of distortion where each signal is passed through a wave shaping function. So it maps each input value to an output value, and each sample is matched separately. So for some input, we look up each sample in our wave shaping function, and then we use that for the output. And what we get is this warped version of the signal. So hopefully, let's listen to what that could sound like. Here's our input sound. Great. And I'm just going to sort of show a couple of possible shapes for this wave shaping function. A classic is the hard clip. So you've got sort of input on the x-axis and output on the y. And you can see that when the input goes beyond certain limits, it just kind of gets capped. And this is what it sounds like applied to our sound. So there's that kind of growly addition to it, particularly when you get sort of the extra chords coming in and multiple notes. You get this cross modulations between different things. Another pretty common shape is a soft clipper. So they also limit the output range, but there's a bit more of a gentle corner to it. Now, personally, I think these sound like vastly different. I think it's quite a subtle difference, but here's an example of what this can be. So another thing, if you're sort of, I would very much encourage you to sort of make up your own wave shapers just because it's a fun thing to do in an afternoon. Generally, if you have some kind of corner or wibble or nonlinear stuff near the origin, then you get a fuzzy kind of sound, because as the signal crosses that, then you get these sort of, extra bumps in the waveform which produce that harshness. And if that bump is near the origin, then that happens for quiet signals or for loud signals. So this gives you a kind of a fuzziness that's independent of the input volume, which I think is kind of sometimes quite useful. And here's what this could sound like. Now, again, I think these roughly produce the same sound, and the main difference with this fuzzy kind of one is that it will do the same for quiet and loud inputs. The next one, though, is wave folding, and you can create all sorts of wild shapes. Wave folding ones where you have a sort of regular pattern are particularly interesting because as the input sweeps up and down, even with simple tones, it will kind of move across these ridges, and you'll get this kind of squelchy sound, almost a little bit like frequency modulation kind of artifacts from a simple oscillation producing these kind of repeated, faster, higher tones. So let's have a listen to that. I can get this right. So that's definitely the most aggressive of all the ones that we've tried so far. But as I say, really, you can try any curve you like. And I would recommend mapping 0 to 0, because otherwise a silent input gives you some DC offset as the output, which isn't great. Now, wave shapers they're very easy to create these bright, harsh sounds. And in my opinion, it's harder to get a more mellow distortion from them. And I think a lot of people spend time experimenting with wave shaping distortion and getting like the soft knee exactly correct to try and get a more mellow sound. But I think that almost any shape sounds brash and bright when you drive it hard enough. And if you don't want something bright and splashy, what can you do? Well, the output harshness is usually in the high frequencies. So one thing you can just do is filter the output. Low pass, that's not very complicated. And the downside of this is that you dull the whole sound. So even if your input is quiet enough that it's not hitting this wave shaping threshold, then the result ends up kind of dull. So to compensate, you can end up brightening the input on the way into the wave shaper. And you can end up with this kind of matched pair style thing. So you do a high boost, like a big high shelf, then your wave shaper, and then a high cut. So you get this wave shaping, and you have this high cut afterwards, which takes the edge off it. And you compensate with this high boost before, which means that the quiet inputs that don't hit the threshold get passed through identically because the wave shaper is kind of linear. So these two filters balance out. Let's have a listen to how that sounds. So firstly, here's our input audio again. If we just put a low pass after our hard clipper, sounds like this. Might be the kind of thing you need to listen for in headphones, but we've lost like just all the high end. I think it sounds a bit dull. We've lost some liveliness from the original input, even as we're adding distortion. Here it is with a 36 dB high boost on the high end, and then the wave shaper, and then a 36 dB cut. So hopefully you can hear that what's happening is the distortion is getting more mellow, because of the frequencies that are added by the distortion, the high frequency ones are getting removed. But anything that's coming through from this kind of clean input is coming through transparently because we've got these matched filters on either side. This matched filter thing is very useful for pretty much anything which gives you these splashy outputs, or overly bright outputs. I always use this if I'm doing a like aliasing kind of sample rate reduction type effect, because then when you have your bass drums that go boom, that translates to really harsh high frequencies, kind of strips the hair off your ears. And if you use this, you do a tilt filter, sort of 12 dB or whatever, and then tilt again afterwards, then you take the most harsh elements of any of these effects, bit crushing, aliasing, distortion, and it really helps. So that's one of my go-to tricks. So if you're writing one of those, I would recommend just enabling it by default as a kindness to your users. But another neat trick that we can use is we can take our wave shaping and rephrase it as an input-dependent gain signal. So here's what our signal flow looks like. I've called this gain shaping because no one has stopped me. And this is what our signal flow looks like. We have our original input coming in along the top, and then we have a second path, which is calculating a gain signal. And as opposed to using our original wave shaping function f, we find some other function, conveniently named g, so that when you multiply the input by that gain, it's the same as the wave shaping. So if you find the right g here, which, I mean, you can just divide, so you can use this equation, but you might find a simpler form of it. This is equivalent, absolutely equivalent to the wave shaping applied sample by sample. So from this perspective, our distortion is now a form of amplitude modulation. The extra frequencies that the distortion adds in now come from the cross modulation between our input and this gain-shaped signal. And the reason this is useful is that we can put a filter on this gain path. So the gain envelope is now smoother, and the amplitude modulation is therefore less harsh. And hopefully you can see how this would preserve the timbre of the clean signal, because, for an input that's not hitting any thresholds, the gain is pretty much constant, and that input just goes straight through. But it also takes some of the harsh elements out of our distortion, our wave shaper, because it's not going to produce any sharp corners in the input that weren't there before, because our gain path is just not changing that fast. So let's compare this kind of timbre to the matched pre and post filter pair that we had. So here is our matched pair, and it sounds like this. Oh, yeah, let's just have a listen to this. And here it is using a low pass on this gain shaping kind of setup. Now, I've tuned those examples so that they match. But still, it's kind of cool they sound similar. So both approaches keep the high end of the distortion down without dulling this, whatever amount of the clean signal is still coming through and audible. So you don't lose that brightness, but you don't add harshness. But one of the advantages of this is it then opens up a whole bunch of creative possibilities. So, if your input has a bunch of strong low end, like your bass drum or whatever, then that ends up completely dominating this gain path. It's all really happens, and you get this often in Waveshapers, that something with a lot of low end just blows out, and you just get this. For this kind of input, you could insert a high pass on the gain path, and what this means is that the wave shaping, which is now gain shaping, is being calculated on a signal which just doesn't have those bass frequencies. So you're kind of taking the bass bits out of the distortion, but again, you're not taking the bass out of the actual input. You're not taking the high bits out of the input. You're just shaping what makes the distortion. So I've used the wave folding curve to illustrate this, because I think this makes the differences really obvious. So here is just the gain shaping with low pass. And I feel I should note that this kind of wave folding produces very harsh sounds. If you're not using this kind of gain shaping setup, you can very easily get a bright splashy mess. And so I think firstly this is quite cool. But if we add that high pass, then the wave folding, which is produced by kind of moving along these ridges in the wave shaping function, when we remove the lowest frequencies, we're now left with the higher frequencies, which are kind of moving across those ridges faster. So let's have a listen. I'll just go back and play those two examples again. So here is the just a low pass. And here it is with the high pass as well. So what's actually happened there is we've made it slightly more brash, but we haven't overwhelmed the high end. That high pass is still doing what we want, and we haven't really cut away anything from the input path. So I think this is pretty cool. And it's not just filters. You don't just need to do linear stuff. So for example, there we are. A fun thing to do is what happens if you put a compressor on this gain path? If your input becomes loud enough to sort of hit this compression threshold, then that gain gets pulled down. So when it goes through the gain shaper, it goes through as if it's quieter. This means you never drive the gain shaper too hard. This setup ends up kind of equivalent to like an adaptive threshold kind of wave shaper, except phrased differently. And I find the controls for this intuitive, but also you could put anything here. I've had fun putting a chorus, but only on the gain shaper, or putting a delay, or other really wacky things, doing different things for different sides, but only on the distortion path, or only on the input. And although there's lots of creative possibilities, the straightforward gain shaping approach here, I like it just because it's a fun shape of signal flow, but it's not completely dissimilar to some of the ways that analog distortions actually work. So you get this thing called, which is like sag on amplifiers, that when they get too tired, basically their output level drops. And that's pretty much what this gain shaping is doing. That when your signal goes outside the range, it can, maybe for a tiny period, actually output what you asked for, but then very quickly kind of like some voltage balances out and it sort of brings it back into the level. But how fast this happens does affect the warmth of the distortion. So even though that's definitely not the way that I like to approach and design audio effects, there is something you can say about this that actually does have some authenticity to it. However, we're not in the analog domain, and therefore it would be irresponsible of me to not mention aliasing. Now, I am not going to do a full explanation of all the things you can do with Waveshapers and anti-aliasing, because that's a whole talk unto itself, and I couldn't do it justice. But what I will say is that if you're oversampling your Waveshaper, which you should, then you can put this whole gain shaping setup inside the oversampling. So if we assume that we have a nice upsampler that doubles the sample rate and leaves that top octave empty, and then say, we'll get to it in a minute, we have a nice gain shaper that doesn't alias. When we multiply the two, we actually don't get any more aliasing. So because the highest frequency of the input is just below the original Nyquist, the highest frequency that the gain shaper will produce without aliasing is just below twice Nyquist. And so the worst it can do is reflect back round to just above Nyquist, and that gets removed by the downsampling filter. So basically, oversampling works with this technique in the most straightforward way possible. But I would also recommend that you use anti-derivative anti-aliasing, which is a very cool trick. Works particularly well even with modest oversampling like 2x. And again, not going to try and explain how that works here. But what I will note is that anti-derivative anti-aliasing delays the signal. So if you use it for straightforward Waveshapers, first order anti-derivative anti-aliasing delays your output by half a sample. Second order delays it by a whole sample. So if you're then recombining this with your plain ungain shaped input, then you might want to delay your input by a similar amount so that you get a nice sample rate independent distortion effect. And yeah, so I'm afraid this was not as in-depth as Ben's fantastic talk, which I'm definitely going to rewatch and use myself. But this was just like a little neat trick, which I thought was quite nice to get, I think, a very friendly distortion. And it's one of my go-to techniques, and opens up a lot of creative exploration and gives you a distortion that's a lot easier, I think, to fit into a mix. And this pre-post filtering is useful for a lot of stuff, but this gain shaper is, I think it's really fun. So yeah, that's the end of what I have. And yeah, if you have any questions, I'm on Discord on the audio programmer Signalsmith, or just email me or anything. So yeah, if there are any questions.
Great. So at the moment, we have one question, and I'll give a couple more minutes for other people to filter in with any sort of questions. Filter, no pun intended. Kostas asks, do these techniques have any advantages in mitigating aliasing?
It's not better than using the same techniques like ADAA or oversampling, but it's not any worse. So using gain shaping with oversampling or ADAA gets the same aliasing as just using plain wave shaping. So the advantage is purely to do with the way that you can craft the tone. It's kind of neutral with regards to aliasing.
Fantastic. Just waiting for any other questions. In the meantime, if you're looking for some great DSP resources, be sure to check out Geraint's website, signalsmith-audio.co.uk. He has several fantastic blog posts. Some people have actually said that they're the most followable explanations for some of these concepts that they've ever seen. And as Geraint said, be sure to join the community, and you can join and ask your questions there as well. He's there as Signalsmith. Looks like that's it for questions. So if we don't have any other questions, I think it's a good time to wrap things up. So thanks once again to our sponsors, Focusrite and Sonics, for sponsoring the Audio Programmer Meetup. Thank you to Geraint and Ben for joining us, especially on such short notice. I had just come off a vacation and I realized I hadn't organized any presenters for the next month, so they came to our rescue at like a day's notice. So thank you very much for that. And as I said before, I will be in San Francisco on the 15th of May for ADCX in San Fran. If you're around, drop me a line. Let's go for a coffee and see what's going on. If you are still looking to purchase tickets, be sure to check out the website audio.dev. And with that, it's time to sign off. The next date of the meetup, I believe, is 13th of June, and we have some a very special event lined up for that I will announce in the next week or so. And yeah, this is awesome. Thank you very much to both of you. Thanks to everybody who tuned in. Yeah, any parting comments from either of you, Ben, Geraint?
Thanks for having me.
Yeah. No, thank you. Thank you once again. And with that, we'll go ahead and sign off. See you all next month. Thanks again for tuning in, and until next time, happy audio programming, happy hunting, and see you next time. Take care, everybody.
Bye.